Kia ora, and here is yet another question using de Moivre's theorem to find the roots of an equation. This one has a little bit of a step up in it, and this was an excellence question back in this year, which was the 2015 paper, in case you guys haven't figured that out already from Google. So first we have to find each of the roots of this equation here. You can't get a much simpler complex cube roots equation than that one. And then we're going to let p be the root in that part with the smallest positive argument, and we've got to show that they can be written like that. Now, this question could have gone on to look at what that means, and you can see that when we've got these are a geometric series, okay? But I'm not going to talk about that much in this video because I'm just trying to smash these all out. But we'll use that fact in some A-level questions, and it actually comes up in scholarship calculus as well. So starting off very quickly, z to the power of 5 is equal to 1 cis 0 plus 2n pi, and we make z r cis theta to the 5. So now we equate r, so r to the power of 5 is 1, r is 1, 5 theta is equal to 2n pi, theta is equal to 2n pi on 5. And I'm just going to chuck in there that's by de Moivre's theorem. Now that's probably actually not quite enough working. We'd better write it out like this. Okay, so just make sure you've got that line in there where you're showing that step there. Because I know that you know what de Moivre's theorem is, but some marker is not going to know that you know what you're doing, so you have to show them. Right, so Z1 is equal to 1. Z2 is where n is equal to 1. It's going to be cis of 2 pi on 5. Z3 is going to be cis of 4 pi on 5. Now I'm going to start working backwards with n equals -1. So I get Z4 is equal to cis of -2 pi on 5, because remember I'm trying to keep my arguments between 0 to pi and 0 to -pi. But for this question it's actually worth noting that when I've got -2 pi on 5, that is the same, that's going that way, but if I go that way, that's the same as 8 pi on 5, right? And I'm doing that because I'm seeing what the second half of the question's got waiting for me, right? And then Z5, where n is equal to -2, is equal to cis of -4 pi on 5, which is equal to cis of 6 pi on 5. So just really badly and quickly sketching those, just so you get this very firmly in your brains. When we have the complex cube roots like this, they will be symmetrically located around the center here. So 2 pi on 5 here. Oh, can I draw it 4 pi on 5 here? Now what have I missed? These are not looking very even at all, guys, are they? So 2 pi on 5, 4 pi on 5, 6 pi on 5, and then 1 down here. Okay, that's a terrible picture, right? They should be even. Let's just get rid of that. So the second half of the question, show that the roots in part 1 can be written as 1p p squared. And p is the root with the smallest positive argument. So the smallest positive argument here is our Z2 value. So p is equal to cis of 2 pi on 5. P squared is equal to cis of 2 pi on 5 squared, which is equal to cis of 4 pi on 5. And that is equal to our root 3. So that's equal to Z3. If I keep going, p cubed is equal to cis of 2 pi on 5 cubed, which gives me cis of 6 pi on 5, which is z what? What was that one? P cubed, I think, is equal to, yeah, so z cubed turns out to be equal to the last one, right? So this is why I wanted to translate it from -4 pi on 5 over to 6 pi on 5. So that's my fifth root, and p to the power of 4 is equal to cis of 2 pi on 5. To the power of 4 is equal to cis of 8 pi on 5, which is equal to cis of -2 pi on 5, which is our Z4. Thanks for watching. I'm sorry these are getting really scribbly and messy. I am just trying to crank them out really, really quickly, so going a bit faster than usual. Please let me know today if you've got any questions. I'll try and YouTube the last couple of excellence ones when I get home later on.